Okay, I am recording now. So okay, right. So again, this is theorem 1A. So which I have displayed to you guys just now. So this is actually again. So this is the thing in. We are still refer back to this chapter 6 supplement. Okay. So in page 1. So first of all, we shall look at the application for this theorem 1A. Just by the way, if you want to make, so this is actually theorem 6.1.3 in lecture notes. Okay. Okay, we will go through several examples to see how to what is the application for this formula, right? Okay, so the criteria is very easy. If we have a set of random variable x, y, or x1, x2, x3 up to xn, so if they are independent, then we have this formula. Yeah. So this is for two random variables. Okay, we have this. So in general, if we have up to n random variables, so we can have this. In general, if x1, x2 up to xn are independent, then we have this. Okay. Phi of x1 plus x2 up to xn. So that is, we just multiplying phi x2 dxn. Okay. Provided only one hypothesis, provided they are independent. Okay, now let's look at two examples. So first one, example 4. Okay, so example 4. Suppose x1, x2, and so on are independent up to n, then and each of the xj having normal distribution with mean mu j and variance sigma j square, then the summating of xj, j running from 1 to n, is also a normal distribution with mean is equal to summation of the mean, and the variance is summating those variance. Okay. All right, before that, just recall this formula. Okay. I think I can just directly write down, just to recall this formula. Okay, so if x is having normal distribution with mean, mu, and variance sigma square, then so its characteristic function is given this way. So okay, I think it's the same. So it's a mu it minus sigma square t square over 2. Okay, just now I think I put it this way, but they are the same. Okay, either one will do. Yeah, so this is where x is a normal distribution. Right? So in this case, we want to prove this, right? So which means this is what we want to prove. So in this question, so we want to show the characteristic function will be equals to this is what we want to show by summating all the xj. T is just following this pattern, that will be E. So you just need to look at these two parameters here. So that is just, we want to show this is equals to 2 okay, this multiplying T minus j square t square over 2. Okay, e power of this whole thing. So this is what we want to prove. Okay, so once we're able to prove the characteristic function for summating xjj running from 1 to n is given in this pattern, then we can make this, we can get this conclusion. So this is one of the application for these formulas here. Right, so now let's look at the solutions for it. Okay, let's do it one by one. First of all, find phi of x1 plus up to xn t. Okay, so because of their independence, x1, x2 up to xn are independent. So this is actually, we can put it as the product of them, x. I think maybe I put it down here. So this is equals to ex1t multiplying x2t multiplying xnt, the product that. Okay. Right, so for the first one, we use back the formula. So this is equals to e of 2 mu 1 t minus sigma square 1 t square over 2 multiplying e 2 mu and so on mu n t, sorry, t missing here, t minus sigma 2 t square. So this is n minus sigma n square t square over 2. Okay, next we just look at the component for t. So I have mu1, mu2 up to here. So we can actually combining all these terms. So e2 of mu1 plus mu2 up to mu n t. Okay, next we can also look at this. So we have a sigma 1 square, which is a coefficient for t square, sigma 2, sigma n square here. Okay, sorry, this is also a square here. Okay, and then we can combine them together. So that will be minus of sigma 1 square plus sigma 2 square, sigma n square, t square. Okay, now we can see the pattern. So this one, and together with this. Okay, so that means we can replace this with our sigma. So this to be our new sigma square. So that means then we can have, hence we can make conclusions. So just to let you know, that means you're going to have the new mu will be mu1, mu2 up to mu n. Okay, and also we have a new sigma square. So it's actually equals to the sum of these things, sigma 1 square up to sigma n square. So using this formula, then we can claim that hence. So the summating of xj, j running from 1 to n, having the normal distribution with the new mu, that is and new variance, sigma 1 square plus sigma 2 square and sigma n square. Right, so this is one of the application for this generating function. if we have a set of independence random variables, so we can actually use these generating functions to identify the distribution for the sum of all those independence random variables. Okay, let's look at another example, maybe the discrete case. So the first one is the continuous case. So let's look at the discrete case. So this one. Okay, so suppose x1, x2, and so on are independent, and each of xi are Poisson distribution with mean lambda. So then the sum of all these xi is also having a Poisson distributions, and with mean is equal to summating all the lambda I. Okay. So in this case, so this is a discrete case. Okay. So in discrete case, so maybe let's use maybe we can use the probability generating functions to solve the problem. Okay, so before that, just to recall the formula, see what can we do if we have a independent set of random variables. Okay, so again, we have a similar formula. So maybe I just put it over here. Okay, this is our theorems. So theorem 3, so which is actually similar to theorem 1. Yeah. So with some additional conditions, actually we do not need the additional conditions for this. Okay. So we have this. Whenever x, y are independent, then zeta x plus y will be equal to zeta x plus multiply zeta y. Yeah, of course, this is only applicable for this is for discrete case only. Yeah? As I said, this probability generating function only applicable for discrete case. So we can use this theorem to solve our problems here. So before that, what we need to do is we just need to recall the probability generating function for Poisson distribution. So if x is a Poisson distributions with lambda, okay, then probability generating functions is given by e lambda z minus 1. Okay. So what you need to do is just need to take notes of this part. Okay. The lambda and the lambda here. So for our case, we want to show this, right? Okay, so we are actually want to show have to be a pause on this. So which means in this case, I want to show this, the zeta of x1 plus xn z must be equals to e of summation lambda 1 plus lambda 2. Okay. So this is what we want to put. As long as we can get the right hand side can be expressed in this way, then the proof is done. Right? Okay, now you know the idea how to solve this. Now we can look at the solution for it. Yeah. So we just need to show this is equals to this. So zeta x1 plus z. So again, as I said, when all these are independent, we can have this formula, okay, or these decompositions. So this is also applicable up to n independent random variable. So that's why this can be written as zeta x1 z multiply zeta x2 and up to zeta xn z. Okay, next we just apply this formula into here. and it turns up to be okay. When this is lambda, so the lambda, but for x1 this is lambda 1, so then we can have this is e lambda 1 z minus 1 multiply e lambda 2 z minus 1 on 2. And I think this is a well-known properties for exponential function. Okay, maybe this just now I didn't put it in, maybe this one. So e a e b is actually e a plus b. I think this is a well-known property. So we are using this. Then this can be equals to e of lambda 1 plus lambda 2 up to lambda m. This. Okay. So actually, we just look at the common terms over here, factor it out. So we have this. Okay, done. We have shown this is equal to this. Then we can give conclusions here. Having Poisson distribution with mean is equals to the sum of all those lambda. Okay, just like that. Okay, so you can actually prove this, solve this problem using the characteristic functions instead of the moment generating function. So what you need to do is you just need to replace the formula for characteristic functions over here and work out the similar calculations. Right, so this is how we can apply this generating functions to independent random variable, okay, to identify the distribution for the sum of independent random variable, okay. So this is a first application for these generating functions. So next, we look at another applications. Okay, so I put it as an example. In fact, this is just for your information. So this is actually theorems 6.2.1 in chapter 6, just for your information. So, but I put it as an example just to demonstrate how to apply this generating function to prove this formula. Okay, we have already discussed this formula in chapter 5. Okay, so here's are the statements. Okay, supposing we have a sequence of random variable xj, I switch the index from I to j is because here I reserve I for I is reserved for the square of -1, so that's why I use j instead of I. Yeah, so xj, a sequence of random xj, j running from 1 up to infinity. So and they are IID, so that means they are all independent and having the same distributions. Okay, again, this is the standard hypothesis. We assume the mean for each of the random variable is 0. Okay, so then we have this formula. Okay, note that this formula, okay, just to remark, okay, note this formula. So valid for random variable with variance, infinity variance. Okay, So even the variance for those random variable are equal to infinity, whether it's infinity or finite doesn't matter, we don't care. So then we can have this result. Okay. In fact, the proof is independent of variance. Do we need Okay, so this is the case here. Yeah, we do not need the variance to be finite here. So this. Okay, so again, independents are having the same distribution. So then with zero mean, so Sn over n will converge to zero in distribution. So the proof is actually not so easy. So we need to apply several formula. Okay. So the first formula that we need is this. Okay. We need this formula. Okay. In fact, again, just to let you know, so this is theorems 6.1.8 in chapter 6. Okay, just for information. So this is the Taylor formula. Okay, as I say. So the general general expression for this Taylor formula would not stated over here. So you may refer to the lecture notes in chapter 6 to look at the full expression for the formula. However, I only look at two special cases whereby the formula for k equals to 1 and k equals to 2. In here, we only need to apply this formula k equals to 2. Okay? So this is the one. So what you need to do is you just need to refer to this formula. Okay. I use a s over here instead of t. So the characteristic function can be expressed in this way. So pxs is equal to 1 plus is ex plus s theta s. Okay, what is this theta x? What is this? So this is a function whereby the limit when x approaches 0, so which is equal to 0. So which means in a way you can say this function theta is having a very small magnitude. So in terms of the language of calculus, right? So this theta is actually the error terms. Okay, for the approximations. For the Taylor approximation. Right. So you may put it this way. So you may say this px is an actual value. So this 1 plus isex is an approximation. So this is the error terms. Okay, the difference between the actual terms and the approximations. Okay. Yeah, we shall look at this second version k equals to 2 formula later. So at this moment we only need this part. Okay. Okay, so again, let's look at our statement once again. So here are all the dates. So our xi are all independent, and exj equals 0, and we want to prove Sn over n converge to 0 in probability. Okay, so what we want to prove will be like this. Okay, maybe you can refer back to this table. So okay, so we just look at this table. So again, this is a table in our, so this is actually in the last table in the last page. Okay. Chapter 6. Okay. All right. So this is the characteristic the tree generating function for constant distributions. Okay. So when the value for x is c, so the characteristic function is e c I t. Okay. When this is c, so this is c I t. So according to here, then this is what we want to prove. We want to show this in these questions. We want to show this. So is equals to e power of 0. We want to show this, e power of 0. E power of 0. We want to show this. So why is that so? Because of e power 0 could be written as okay, could be put it as e I t multiplying 0. Okay, e power of 0 could be written as e I t multiplying 0. So which means then this is the c here. Then in this case, once we're able to show this, the limit for phi sn over nt is e0. So then from here, then we can see that this Sn per n will converge to 0 in distributions. Okay. In fact, this is actually means our C here. Okay, so this is what we want to show. Okay, first, so maybe this is the, I would say this is the first step number 1. So we want to show this is equal to this. Okay. However, if you go back to the question is a bit different. So it's actually want to show this is a converge in probability instead of in distributions. So how to do this? So because we are not having the same thing. So what we can do is again, so you may refer back to what we have discussed in chapter 5. Just 1 minute. Just 1 minute. Sorry. So I hope you you guys can remember this picture, this diagram. Okay, so just to for environment. So this is the diagram. In page 1 of chapter 5, sub A. Okay, so I think you should know this. Okay, so this diagram actually gives you the relationship among the 5 convergence. So what I interested is actually you just need to focus to here. Okay, I think maybe just here, just this one. Okay. Okay, so if you look at here, first step, we can show that this one is equals to E0, which is equals to EIT0. So this just simply means that Sn over n will converge to 0 in distributions. Okay. Okay. However, if you look at here, Xn converge to X in distributions when, as a special case, when X is equal to C is a constant, then we actually can reverse process. Then we can say that Xn will converge to X in probability, provided that X is a constant. So it so happens that in our case, 0 is C, which is a constant. Then we can actually apply this reverse process. Okay, so that's why using this, that's why send to this one, then we can imply that, and we will set to, hence we can conclude that Sn over n converge to 0 in probability. Okay, by using this process or this property. So if the limit distribution is not constant, then this conclusion might not be true anymore. Yeah? So it so happens that the limit is constant, so we can use this reverse process to make such a conclusion. Okay, so I hope you guys can understand the idea for the whole proof. Actually, it's quite complicated. We have to go through several processes as well as applying several concepts to do it. Okay. So I hope you can get that. So actually, the main calculation will be here. We just need to show this one equals to this, and then we can do it. Right. Okay. So now we can do our calculation now. Where is my? Okay. So I think maybe let's do it once again. Okay. I hope you can get a picture. So, or you can get an idea for the solution. At least you know what we're trying to do now. Okay, let's look at the solutions. Okay. Okay. First of all, we can have this. So this is actually equals to this E of EIT Sn over n. Okay, so then you can combine the parameters. So that will be these two scalar EI of T over n multiplying our Sn. So you may replace this to be our new parameter. So therefore, so we can let this to be, let's say S, then this will be equals to mention phi Sn of T over n. Okay. So again, we just let this one to be S. So this is the way. Okay. So we know this. Okay, now we can continue. So this one is equals to Sn is actually summating all the Sn. So therefore, we can say this is a phi of S1. S, okay, maybe. Okay, so here I just make it easy. I just simply write S to be T over N to simplify our symbol. Okay, so and because all these are the same distribution, so therefore you can say this is a x1 of s, then power of n. Yeah, so this one is because you can see because x1, x2, and so on are IIT. Yeah, they're having the same distribution. Oh, sorry, this is not s, so this is actually n. Okay, find x1s. Okay, next things. So maybe I cut and paste the formula once again since it's too far away from things. So just to put our formula once again. Okay, here is our formula. Copy once again. Maybe let's give it this. Okay, so again, phi xs is equal to 1 plus I s e x plus s theta s. So what is this theta s? So this theta s is the error terms having these properties. Is limit of x to 0, theta s is equal to 0. Okay, so then we just need to substitute this into here. And also, because of the mean is equal to 0, so therefore this one can be written as 1 plus 0 plus s theta s. Okay. So this one 0 is because of, we know that because e of xj are all equal to 0. So that's why we got 0 here. Okay, again, we have of n here. Okay, okay, power of 0. Sorry, 0 here. Then we can write this one as 1 plus 0 divided by n. I think 0 is equal to 0 multiplied. So, and then we can something like plus n of n. Okay, here what we can do is we can just use some kind of the multiplication. So we have s over theta s according to our thing. So this is t over n over theta of t over n, right? So then we can combine this thing together. So then this will be equals to t over n. Okay, so that's why this yellow color one, so this one will be just represented by another phi of n. Okay, why we want to put it in this pattern? So again, we need to recall another formula here. Okay, so for your informations, so this is actually remark 6.2.1 in chapter 6. Okay, so this remark 6.2.1 give you this formula. Okay, this formula, so you may use this formula without proof. So if you have this expression 1 plus a over n plus this again phi n over n of n. So limit of n to infinity, so this is EA when a is a constant and this one is 0. So it so happens that 0 is a Okay, so that means this is our 0. Okay, is our 0. And this one is having this property. We also have this property. So using this formula, then we can see that. So we have this limit n to infinity of p s n over n t is equal to limit n to infinity of this 1 plus 0 over n plus so that is equal to e power of 0. Okay, so this is what we can prove by using all this formula here. Okay, so this is e power 0. Okay, so maybe let's go back to our discussion at the moment before this solution. Okay, so now we can apply these arguments over here. Okay, I think done. We have done this already. We have shown that this limit phi Sn over n will be equal to EIT0 E0. Okay, so then immediately by using theorem, we can see Sn over n will converge to 0 in distributions. Okay, so and next we make use of this formula, and which is actually a theorem in chapter 5. Okay, so then we can conclude that Sn converge to 0 in probability. Okay, then we can come to this.